Okay, good afternoon, everyone. Welcome to the fifth webinar of the IMath Webinar series for this semester. Okay, before we start, let me remind everyone that this Zoom meeting is being recorded and it is being streamed live on YouTube, and the link is posted on our Institute of Mathematics official Facebook page. Okay, so again, I'm Gina Angelo Velasco of the Institute of Mathematics, and today we are joined by Dr. Janine Concepcion Arias of the Discrete Geometry and Combinatorics Group. Dr. Arias recently finished her PhD under the supervision of Dr. Manuel Joseph Loquias, and today she will present her work titled Similarity Isometries of Point Packings. Okay, so let us all welcome Dr. Janine Arias.
Hello.
Good afternoon, Dr. Arias. Okay, so
Good afternoon, sir.
okay, so you can start. Yes, you are co-host, so you can share screen.
Okay, thank you. Hello.
Yes, we can hear you.
Ay, okay po ba, sir?
Yes.
Bakit parang tumigil po yung video ko? Nangyari? Hello? Wait lang
Hello.
po.
Yes, nakalagay.
Ayan, okay. Naghang
Okay.
ako. Okay na.
Okay, so
Ayan,
it's good.
okay.
Okay,
Ayan, so, good afternoon, everyone. Ayan. Today, I will talk about similarity isometries of point packings. So, this was part of my dissertation under the guidance of Dr. Manuel Joseph Loquias. So, let us begin by discussing the notion of similarity. Two sets are similar if one is the image of another under a similarity transformation. So, a similarity transformation involves rotation or reflection, uniform scaling, and translation. In other words, two geometric objects are similar if they have the same shape, but not necessarily the same size. For lattices, the shape of the lattice is described by the Bravais type of the lattice. So here we have the Bravais types for two-dimensional and three-dimensional lattices. So for example, let us consider the square lattice Z2, here identified by the ring of Gaussian integers Zi and represented by the white dots. If we rotate this lattice about the origin at an angle of pi/4 and apply a scaling factor of square root of 3, then we will get the pink dots, which represent alpha r gamma. And clearly, we can see that it is also a square lattice. So upon applying a similarity transformation, the Bravais type or the shape of the lattice is preserved by the similarity transformation. And we say that the lattices gamma and alpha r gamma are similar. The set of similarity transformations of a lattice can only form a monoid at most, meaning it's almost a group, except it is not closed under inverses. But if we exclude translations and only consider the set of rotations or reflections, then the resulting set of linear isometries will form a group. This linear isometry satisfying this condition is referred to as a similarity isometry, and that is what we want to study. Similarity isometries have applications in crystallography, particularly in the study of color symmetries of crystals and quasicrystals, and self-similar structures like fractals and tilings with singularities. They were also used in the field of data compression in the design of multiple description lattice vector quantization. Similarity isometries may also be viewed as a generalization of coincidence isometries, which are used to study grain boundaries of crystals. And from a theoretical standpoint, the group of similarity isometries and the group of coincidence isometries are mathematically related. So let us now proceed to define a similarity isometry formally. For this, we define the following. A lattice is the z-span of b linearly independent vectors in Rd over R. In other words, for any basis of Rd, the subgroup of all linear combinations with integer coefficients of the basis vectors forms a lattice. Or we can also say that a lattice is a subgroup of the additive group Rd, which is isomorphic to Zd and spans Rd. So a sublattice of gamma is a subgroup of gamma of full rank, meaning with finite index in gamma. Linear isometry R is an orthogonal linear transformation in Rd. So examples are rotations and reflections that fix the origin. So now let us define a similarity isometry. A linear isometry R is a similarity isometry of a lattice gamma if there exists a positive constant beta such that beta R gamma is a sublattice of gamma. So we will use the symbol to denote a sublattice. Geometrically, this means that after rotation or reflection and uniform scaling, the transformed copy of the lattice must be contained in the original lattice. So here the set beta R gamma is called a similar sublattice of gamma. Alternatively, we can define a similarity isometry in the following way. R is a similarity isometry of gamma if there exists a positive constant alpha such that the intersection of gamma and alpha R gamma forms a sublattice of gamma and alpha R gamma. So we denote this relation by tilde. In any case, the group of similarity isometries of gamma is denoted by OS of gamma and it may be defined using either definition. So we are also interested in the set of scaling factors. We may define two sets of scaling factors, namely big skull and small skull, corresponding to the two definitions earlier. So big skull is for this definition and small skull is for the second one. So by definition, the sets of scaling factors are non-trivial if and only if R is a similarity isometry of gamma. We also define the denominator of R to be the smallest scaling factor, beta, smallest positive scaling factor, beta, such that beta R gamma is a sublattice of gamma. So it is known that elements of big skull and small skull are just integral or rational multiples of the denominator of R. So let us illustrate the distinction between the two definitions here and big skull and small skull using the following example. So here, the white dots represent the original lattice, which is the square lattice Zi. The colored dots represent the transformed copy of the lattice. So that is beta R gamma for the blue dots and alpha R gamma for the orange dots. So where beta is square root of 5 and also equal to the denominator of R, while alpha is square root of 5 over 2. So in letter A, the transformed copy, meaning the rotated and scaled copy of the lattice, is a sublattice of the original lattice. So this illustrates the first definition. And beta is therefore in big skull gamma. Meanwhile, for letter B, the transformed copy has points that do not intersect the original lattice. So in this case, the intersection of gamma and alpha R gamma is the one that forms a sublattice of gamma. So the intersection of gamma and alpha R gamma is represented by the intersection of the orange and the white dots. So here. And this illustrates the second definition. And alpha is in small skull of gamma, small skull gamma of R. So this is the difference between uh, the first and the second definition and big skull and small skull. So similarity isometries and similar sublattices have been studied by mathematicians in the past. Here are some recent papers in the related literature. Various papers have explored similar sublattices of certain lattices up to 4 dimensions. And mathematically, similarity isometries are related to coincidence isometries. So there have been studies about their connection and about combinatorial problems arising from these topics. Coincidence and similarity isometries were also extended from lattices to modules and from lattices to point packings. So the extension of similarity isometries to point packings is what we are interested in. So let us now discuss what a point packing is. A point packing is the union of a lattice gamma with a finite number of shifted copies of gamma. And point packings are also sometimes called crystallographic point packings or multilattices by some authors. Point packings serve as models for ideal crystals, that is, crystals with more than one type of atom per primitive unit cell. Examples include the hexagonal packing or the honeycomb lattice, the diamond lattice, which describes the crystal structure of diamond, tin, silicon, and germanium, and the hexagonal close packing, which describes the crystal structure of quartz. So we will write a point packing L in this way, where x naught is always set to 0. Here, gamma will be called a generating lattice of L, and the shifted copies of gamma, including gamma itself, will be called components of L. The components should be distinct from each other. Also note that point packings are not necessarily lattices because they do not necessarily form a group. For example, here we have the hexagonal packing. It is the union of the hexagonal lattice represented by the black outline dots and its shifted copy by X, represented by the gray outline dots. So the union of the black and the gray outline dots comprises the point packing L, which is the hexagonal packing. The hexagonal lattice is identified with the ring of Eisenstein integers Z omega, where omega is the complex number e to the 2 pi I over 3. And here, the hexagonal packing has two components, gamma and this shifted copy of gamma. So as we can see, the hexagonal packing is a point packing, but it is not a lattice because it lacks the center points of the hexagons. And therefore, it does not form a group. So now our goal is to extend the notion of a similarity isometry to point packings. And for that, we must define the following. So a subpacking of L is a subset of L with finite index in L. And by index of L prime in L, we mean the ratio of the density of points in L by the density of points in L prime, or in other words, the number of points of the generating lattice of L in a unit cell of the generating lattice of L prime. So here we assume that the generating lattices of L and L prime have the same rank, and hence the index of L prime in L is finite. So now we can define a similarity isometry of a point packing. A linear isometry R is a similarity isometry of L if there exists a positive constant beta such that beta RL is a subpacking of L. So we denote this by this symbol again. So here, beta RL has finite index in L and is called a similar subpacking of L. We also follow similar notations for the set of similarity isometries and for the set of scaling factors. So this time we put L here instead of gamma. And we use big skull for the set of scaling factors. So what we want to do next is to characterize the similar subpacking beta RL by identifying its components. For this, our strategy will be to examine the intersection beta RL with L component-wise. So in other words, we want to examine the intersection of a component of beta RL intersected with a component of L and check all possible non-empty intersections. It turns out that such an intersection is either empty or it's just a shifted copy of this intersection of gamma and beta R gamma, where gamma is the generating lattice of L. So from here, we are able to provide a characterization for a similarity isometry of a point packing. And it's given by this theorem. So essentially, this result tells us that beta RL is a similar subpacking of L if and only if every component of beta RL intersects a fixed number of components of L. And this fixed number is n, where n is just equal to the index of gamma intersection beta R gamma in beta R gamma. So here, n can be at most m where m is the number of components of L. So the result implies that OSL, so that's the set of similarity isometries of L, is a subset of the set of similarity isometries of the generating lattice of L, which is gamma. Also, we have the set of scaling factors with respect to L is contained in small scale gamma. And we can improve this subset relation by replacing small scale with 1 over n big scale gamma, where n is the index that we mentioned earlier. So let us dive further into this number n and consider the case when n is greater than 1, meaning the case when each component of beta RL intersects more than one component of L. So to illustrate n greater than 1, let us have this example. We take gamma to be the 3 by 1 rectangular lattice here. So given by the black outline dots here, here, here. Okay. And consider its shifted copies, 1 plus gamma given by the gray outline dots. So you have this one and 2 plus gamma given by the red outline dots here. Then the union of the black, gray, and red outline dots forms the point packing L, okay, which is actually just the square lattice Zi. And let's also consider beta equals 1 and r to be the rotation by 90 degrees about the origin. So if we rotate by 90 degrees about the origin, then what will happen to our black, gray, and red outline dots? The black outline dots will go to the blue dots. Okay. So gamma will go to beta R gamma here, blue dots. And then 1 plus gamma, the gray outline dots will go to the yellow dots. So that's beta R of 1 plus gamma, or orange dots. And the red outline dots, 2 plus gamma, will go to the green dots. Okay, so those are the components of your beta RL. And beta RL is just the union of the blue, orange, and green dots. But as we can see, beta RL is just equal to L. And that is expected because the 90-degree rotation is a symmetry of the square lattice. So observe that the blue dots intersect the black, uh, gray, and also the red outline dots. So the same is true for the orange and for the green dots. So in conclusion, each component of beta RL, so each of these, intersects 3 components of L. So the black, gray, and red. And therefore, n equals 3, which is greater than 1. So let us now look at the case when uh, n equals 1 So in this case, each component of beta RL intersects exactly one component of L. A sufficient condition for n equals 1 is when beta is in big skull gamma. And thus we have the following corollary of our previous result. Here, each component of beta RL intersects exactly one component of L. And the planar examples that we will discuss later fall under this case. But before we go there, let us look at this example of n equals 1. So here, notice that the colored dots intersect only the black outlined dots, meaning all components of beta RL, the blue and orange dots, they only intersect gamma, okay, and not x plus gamma, the gray outline dots. This tells us that components of beta RL may be contained in the same component of L, or in other words, the subset relation between the components of beta RL and the components of L need not be one-to-one. So let us now examine the properties of the set of similarity isometries of L. First, the identity isometry is in OS of L. Next, closure under inverses remains unsolved. And for closure under composition, we have a sufficient condition. So this one. And the converse of this result does not hold. So counterexample is the previous example where n is greater than 1. So under this sufficient condition, uh, the set OS of L is at least monoid. So let us now introduce the following notation to help us identify the components of beta RL. So the components of beta RL are determined by identifying the pairs xk, xj of shift vectors of L, satisfying the theorem earlier. So, and in other words, tau of beta RL here collects all the pairs that correspond to non-trivial intersections of components of beta RL and components of L. In other words, tau is this collection of all pairs that correspond to non-empty intersections of beta Rxk plus gamma intersect with xj plus gamma. So in particular, if beta is in big skull gamma, then our n will be equal to 1. And we will have this simpler result, which will be used in the following examples. Namely, we will have the 1 by 2 rectangular lattice and the hexagonal packing, which are generated by the square lattice and the hexagonal lattice respectively. As mentioned earlier, uh, these point packings fall under the n equals 1 category. So what we will do is we want to compute for OS of L and the skull for each of these point packings. For that, notice that uh, we will take note that they satisfy these 2 point packings. They satisfy the property that all its shifts have rational components. And because of that, we have this result that OS of L, or the set of similarity isometries of L, is just equal to the set of the group of similarity isometries of uh, the generating lattice gamma. Therefore, for these two examples, OS of L is a group. And meanwhile, for the skull and the tau, we show the following results. So let's begin with the 1 by 2 rectangular lattice, which may be viewed as a point packing generated by the square lattice Zi. Okay, so it's the union of the square lattice and this shifted copy of the square lattice by 1/2. So this table here shows the skull and the tau for all possible similarity isometries of L. The similarity isometries here are classified according to congruence modulo 2 of the real and the imaginary parts of the complex number. So the complex number associated to our rotation R. And here reflections are represented by their rotational part. And when the entry for skull consists of 2 rows, it means that skull is equal to the union of those 2 sets. So we just write it in different rows because they generate different taus. And meanwhile, to interpret tau, for example here, the pair 1/2 0 means that beta r 1/2 plus gamma is a subset of gamma. Here, 1/2 means beta r 1/2 plus gamma is a subset of 1/2 plus gamma. So for example, consider the rotation r about the origin by tan inverse 2. So this rotation corresponds to multiplication by the complex number 1 plus 2i over its modulus, which according to the table is classified under this row because you have 1 mod 2 and 0 mod 2, okay, for your a plus bi. And moreover, if we consider the scaling factor square root of 5, which is actually equal to the denominator of r, then we are classified under this category for skull. And thus we get tau for this example. So to illustrate, we have the following figure. So here, L is the 1/2 rectangular lattice, which is just the union of gamma, uh, the black outlined dots, and 1/2 plus gamma, represented by the gray outlined dots. Okay. So meanwhile, beta RL is represented by the blue and the orange dots, where the blue dots represent beta R gamma and the orange dots represent beta R of 1/2 plus gamma. So the union of the blue and orange dots is your beta RL. And as we can see, the blue dots intersect the black outline dots, while the orange dots intersect the gray outline dots. That is, beta R gamma is contained in gamma, while beta R 1/2 plus gamma is contained in 1/2 plus gamma. And that verifies our result from the table from tau. And thus, beta RL is a similar subpacking of L. And note that not only is beta RL contained in L, beta RL also has the same shape as L, as it is also a 1/2 rectangular lattice, but it's just rotated and scaled. So next here is the table of results for the hexagonal packing. This table is for the similarity rotations. A similar table may be computed for the similarity reflections. And again, just as expected from the general result, the tables confirm that OS of L is equal to OS of gamma, and OS of L is a group. So as an example, let us consider the 60-degree rotation about the origin, which corresponds to multiplication by the complex number 1 plus omega over the modulus, okay, where here omega is, again, the complex number e to the 2 pi I over 3. Let's also consider the scaling factor 2. So according to the table, we have to look at A plus B omega. So in that case, you have A and B equal to 1. So the sum will just be equal to 1 plus 1 equals 2, which is 2 mod 3. While beta equals 2 falls under this category because the denominator of R in this case is 1. And thus we have the following tau. And to illustrate this, we again look at the figure. So here, L is the hexagonal packing represented by the black and gray outline dots, while beta RL is represented by the blue and orange dots. So we can see that the blue dots intersect the black outline dots, while the orange dots intersect the gray outline dots. So again, this verifies the result that from the table, we have beta R gamma is a subset of gamma, and beta R of the shifted copy of gamma is a subset of the shifted copy of gamma. So here you have that same result verified by the figure. So the beta R gamma is contained in gamma, while beta R of the shifted copy of gamma is contained in the shifted copy of gamma. And thus, beta RL is a similar subpacking of L. For the last part of our discussion, let us now consider rotations about points different from the origin. So recall that what we have been doing so far is we rotate point packings about the origin because by definition of linear isometry, the origin must be fixed. So now if we want to rotate a point packing about a point different from the origin, say we want to rotate this point packing at negative x. So instead of the origin, we want to rotate about this point negative x. Then notice that this problem is just equivalent to this one, okay? Which is just what we do is we translate all points of the point packing by x, and then we rotate about the origin. So in other words, we may simply consider linear isometries of x plus L, or we consider the translated copy of L by x. And this motivates us to study what we will call shifted point packings. So if L is a point packing, then x plus L is given by this union. Observe that x plus L is still a union of shifted copies of gamma. So it is similar to a point packing in that sense. However, the only difference is that the shift vectors of x plus L are now x plus xk. So meaning they are now shifted by x. So before we only had xk plus gamma, now we have x plus xk plus gamma. And moreover, x plus L does not include gamma and the origin because as we said earlier, x0 is always set to 0. So instead of having gamma, we will now have x plus gamma our as a component, no, instead of gamma. And also the origin is also not included in this set. So nonetheless, this is still a union of shifted copies of gamma, and hence we may still apply the results for point packings to shifted point packings. So let us show an example using a particular shifted hexagonal packing where we will use x equals 2 plus omega over 3. So we just add 2 plus omega over 3 to each component of our hexagonal packing before. Okay, so this table shows the result for similarity rotations, and a similar table may be computed for similarity reflections. From the tables, we may conclude the following, that the set of similarity isometries of the shifted point packing x plus L is a proper subgroup of the set of similarity isometries of L, which, by the way, from what we said before, is equal to the group of similarity isometries of the hexagonal lattice, the gamma. So what does this imply? It means that, so consequently, there are similarity isometries of L which are not similarity isometries of x plus L. In other words, there are more similarity isometries of the hexagonal packing when one rotates about a vertex of a hexagon than when one rotates about a center of a hexagon. So this is a surprising result since the hexagonal packing has more symmetries about the center of of a hexagon than about a vertex of a hexagon. So here's an illustration. We will again consider the rotation R to be the 60-degree rotation, but this time we use a different scaling factor. Here we take beta equals 1. So so now we have the shifted point packing. So that's why it looks like this, no? So we have x plus L, and we rotate about the origin using the 60-degree rotation. So since R is the 60-degree rotation about the origin, it is clear that beta R x plus L is equal to x plus L itself. Okay, so if you rotate about the origin by 60 degrees, then you will just, all the points will just go to the same set of points. Okay. So let us now compare this with the previous example of the hexagonal packing. Okay, so this is what we had before. This is the hexagonal packing L. And now here we have the shifted point packing or the shifted hexagonal packing. So note that the 60-degree rotation R is a similarity isometry of both the hexagonal packing L and the shifted hexagonal packing X plus L. Okay, since OS of X plus L is contained in OS of L as we have mentioned earlier. However, based on the previous tables for this example and for this example, the sets of scaling factors obtained will be different. And also the denominators will be different. So for example, here, the denominator with respect to L is 2 for the 60-degree rotation. But for the same rotation, the denominator with respect to X plus L is equal to 1. So they're different. And so that's the difference between using the hexagonal packing versus the shifted hexagonal packing. And finally, here are some topics that remain unsolved and are recommended for further studies. So more examples for n greater than 1 case, conditions for the set of similarity isometries of L to be a group, and the existence of a non-group OS of L, because so far the examples that we have are all groups. And that's it. If you're interested in reading the full article, you can find it in the journal Acta Crystallographica, section A. Thank you for listening.
Thank you very much, Dr. Arias. So let us all give Dr. Arias a round of virtual applause. Okay, so the floor is now open for questions. Do we have any question from the participants or from the audience? Okay, actually, Dr. Arias, I have a few questions. Because lattices also play a part in what we're doing in time frequency analysis. So, well, first question, actually, minor na. Nakita ko dun I saw on your slides that, so the X, for example, that you're considering is in RD. So in general, this is applicable for dimension greater than 1, right?
Yes, sir.
Okay. And you've also constructed examples, for example, in 3D, or most of your examples are only in 2D.
Meron na pong, there is already an example that in 3 dimensions, in particular the diamond packing. So it's part of my dissertation under Dr. Loquias. For the diamond packing, we were able to solve for the set of similarity isometries in the skull and the tau. So similar to these tables. Something like that. Similar to this.
Okay, interesting. Thanks. And just another question. Are there conditions under which a point packing can be classified as or can be a lattice?
Classified as
so yeah, under which conditions are point packings also lattices actually?
Also lattices. If well, I think as long as you form a group, but I'm not sure if that's the only. I, I think if it forms a group, I think that
Okay, yeah, it's okay. It's just I was just curious about that.
But yes, no. Mm, there was a result from the dissertation of uh, Dr. Estiliore. It was about wait, it escapes my mind right now. But I think there's a related result. I don't know. It's not for. No, no, I think that's a different one. It's not for classifying point packings as lattices, but rather to writing point packings using the minimal generating lattice. I think that's a
Yes,
different. Yes.
okay, it's okay. Sorry, I was just curious, so it may be beyond the scope of what you did already. Okay.
Yes.
Are there other questions or comments from the audience? Okay, so okay, so here's something from Dr. Lokias. If the minimal generating lattice is the entire point packing, okay, so then point packing is a lattice. Okay, so
Yes.
thank you. Any other question? Okay. So if there's none, let us thank again Dr. Arias for giving us this interesting talk. So let us again give her a round of virtual applause. Thank you.
Thank you.
Thank you, Dr. Arias.
Thank you, sir.
Okay, so the next webinar will be on April 3, I think. Yeah, April 3. And we will be hearing from the optimization and approximation group. So thank you everyone for being here, and I will see you again next time. Okay? Goodbye. Thank you. Okay, I'll end this. Thank you very much.